Hello, everybody. Thank you for being here today. Appreciate you coming to the afternoon sessions. We got three really good presenters for you today. First up is going to be Felix Lalonde Hendershot. Slaughtered that middle name. His background is in mechanical engineering, has worked at Novatech Analytical Solutions for the past 7 years in the design of sample conditioning systems and in technical sales. Outside of work, he likes fly fishing, smoking brisket, and brewing beer. So please welcome Felix.
Thank you so much. Awesome, thank you all. I just heard my bio and fish, meat, beer. It's pretty basic stuff. Could have done better, so thanks for having me. Today's presentation is on the purged lip sealing valve by a company called CV Products, a division of AS Devices. You guys will notice I am none of those three gentlemen listed. I'm actually from Novatech, so this is not necessarily my product. I will do my absolute best to present it to you guys and yeah, take your questions afterwards. So the agenda for today, we'll start off discussing conical rotary valves as well as diaphragm valves, two very typical valves in the injection for gas chromatography. We'll dive into what actually is the purged lip sealing valve, PLSV for short. You'll hear me refer to that quite a bit. We'll compare the PLSV to diaphragm valves in GCMS applications, and then we'll do a deep dive in ultratrace impurities and reactive compounds by GC-EPD technology. We'll wrap everything up in a quick conclusion. So, okay, two types of valves. First one, conical rotary valves. These ones, let's picture them, a cone, rigid cone, pressed into a socket. There is a rotating element that allows for injection. What advantages do conical rotary valves offer? Well, they offer constant flow and pressure, basically no pressure drop, sorry. They also have no dead volume, which is a huge advantage in the injection of sample. Defaults, though, well, they can be prone to leaks, especially without a purge, and they are fast wearing. So that insertion of the rotor, of the conical rotor inside the socket needs a lot of pressure to guarantee the seal, which results in fast wear. Fast wear also means that inert treatments are not really possible when it comes to rotary conical valves. The next type is diaphragm valves, quite common in the industry. Main advantages when it comes to UHP, ultra high purity applications, is really good lifetime. They'll last between 500,000 to 1 million actuations, and they offer really good leak integrity with a purge, of course. Major downsides are pressure and flow drops, them being not constant through the actuation. Diaphragm valves also contain dead volumes. We'll dive into that a little further. And over time, through the flexibility of the diaphragm, it changing through the life of the valve, we can observe peak shifting, which is also an issue we'll observe. So you've heard me mention leaks. There's actually three types that we'll explore individually. Inboard, which is basically out to in, outboard into out, and then crossport, which is contamination between ports within the valve. Inboard leaks, by far our biggest challenge when it comes to UHP applications. And I mean that especially when it comes to the trace measurement of permanent gases, oxygen, nitrogen, so very high concentration in ambient air. Inboard leaks are gonna cause peak shifting and also basically increased noise and decreased detector sensitivity. You'll notice also on the diagram that we point to CO2 and moisture ingress leading to column pollution. Outboard leaks are especially problematic when we're dealing with highly reactive or flammable samples, such as silane, but also toxic compounds. Any leakage can become a risk to operators and have to be managed. Lastly, we do have crossport leaks. Crossport leaks especially involve small molecules, hydrogen, helium, that can lead to contamination. They can accumulate in the column, cause separation, and especially baseline or sensitivity issues. So, where in conical rotary valves? What CV Products did is they actually tested the performance of a conical valve, in this case actually a conical valve without a purge, at different steps of its lifetime. So they've tested performance, or let's call it leak rate, with a brand new valve. They've then taken the valve outside of the analyzer, actuated it 5,000 times through a rig, and then tested again. They saw 2 ppm leak rate, 5,000 more actuations, 50, 5,000 more, 150. The conclusion is basically that conical valves cannot be used in UHP applications, especially without a purge. If we look at diaphragm valves, different issues. It's not necessarily where. Basically, it's all about the diaphragm, and the diaphragm with UHP applications. So diaphragm valves are pretty sensitive to variations in port pressure. Variations in port pressure are going to affect directly the carrier gas flow velocity, and therefore affect baseline variations. We mentioned it before, but through the lifetime of the valve, we'll experience different flexibility of the diaphragm, which then results in peak shifting. I'll skip the last point, just for fun. Dead volumes in diaphragm valves. This one's actually a bit more interesting to dive into frame by frame. I'm not sure if you guys can see it properly, but we'll try. In pink, we've got sample, and in blue, we've got carrier gas. Frame A, let's call it, is basically the valve in ready to inject mode. We find our sample loop full of sample, and as we start the actuation, we will inject our carrier gas through the loop, thus pushing sample towards the column. You'll notice that as we move to frame C, DV1, and I wish I had a laser pointer, but DV1, if you can spot it, actually dead volume 1 becomes filled with pink sample. And as we close the valve, carrier gas starts pushing that sample located in that dead volume towards the column, and therefore towards the detector. How do we address this in UHP applications? Well, introduce the purged lip sealing valve technology, PLSV, sorry. This valve was invented actually by CV Products. It's a valve that offers no leaks, and we're talking no inboard, outboard, or crossport leaks. It's got a long lifetime, proven 3 million actuations in UHP applications. It offers constant pressure drops, basically using a rigid rotor on a flat surface, no dead volumes due to basically having no unswept volumes. Go to the next slide, and we'll start explaining how this works. So, in essence, you find 2 major components. You've got the machine metal body with purge ports that we'll explore later. And to the bottom right, you guys will find a picture of the rigid rotor actually machined out of PEEK. Every green surface is actually the points of contact between the machine block and the rigid rotor. The reason we're able to offer lifelong, or 3 million actuations with really good wear resistance, is the fact that the tolerance of that rigid rotor is so good that we don't need excessive pressure to maintain a good seal. To the top left, you guys will notice the purge in question. So we actually use carrier gas to introduce through various channels constant flow of purge, and we're talking tiny flow rates, but still we are sweeping away any possible leak, inboard, outboard, crossport. This frame actually explains it really well. You will see in teal actually the purge coming into the center of the valve, being swept through channels to the outer lip, and thus preventing our leaks. I'm not sure if you guys can see that, but there's one sole lonely dark spot near the cluster. This is actually our purge outlet. So we capture the flow of carrier gas and any possible leak that occurred within the valve. Having a valve that has low friction offers the possibility for treatments, and treatments are especially important when it comes to reactive gases, especially at low levels. You guys see basically the hue of a sulfoner, I guess, coating in this case. Oops, sorry, went too far. And yes, here we're just showcasing that this valve has been designed to be compatible with various third-party systems, actuators, and whatnot. So, we like independent tests. This is what they did. They basically sent two valves, a standard diaphragm valve as well as a PLSV valve to a company called Focused Photonics, FPI, and they tested on a GCMS for VOC analysis. All parameters were identical. What they found was these two comparisons, basically on top, the diaphragm valve, and on the bottom, the PLSV. This is a little bit particular, but every 200 seconds, we will actually change state. So on, 200 seconds later, off, repeat that again. We'll see on the top diagram that after 120 seconds, we notice our first expected peak of air sample. After the off position, 120 seconds later, we experience a smaller, but still present peak represented by, well, it's basically our dead volume, the dead volume we explored earlier. We also can notice pressure drop effects due to the diaphragm. And if we look to the bottom diagram, we notice that the PLSV does not basically have any of our dead volumes or pressure drop effects. This is basically the exact same slide explaining it in further detail, a zoomed-in version of the off step where we can compare diaphragm to PLSV and the various dead volumes and PLSV explanation. Okay, now reactive compounds. CV Products is a division of AS Devices. AS Devices came up with their own detector technology called the Enhanced Plasma Discharge, or the EPD technology. It is especially good for ultratrace measurements. We're talking sub-ppb levels of LODs for impurities with helium plasma, as well as low ppb level, LODs for argon carrier. They integrated all of that inside their own platform and came up with these results. In this case, they tested samples of moisture and proved excellent linearity as well as stability at fairly low levels. They then carried on a similar test with other reactive compounds, sulfur-based in this case. I won't necessarily go through those, but we're talking ppb levels of various compounds, and again, proved excellent linearity as well as stability. I forgot to mention, but this, of course, was obtained with a coated PLSV valve. Those results would never be possible without such coating. And then you've heard me talk about ultratrace. What does ultratrace mean? They tested 700 ppt sample of nitrogen. It's pretty tough to obtain a 700 ppt sample. They did so with their IGCS dilution system based on sonic orifice technology, and obtained very impressive results for such a low level of nitrogen. And again, performance through the lifetime of the valve. They tested, apologies, PLSV valves after 1 million actuations. So the way they did this is they used a brand new valve, calibrated the analyzer at 1,000 ppb, and then swapped in the used valve, or 1 million actuations, and then proved excellent results through the five samples listed. They also tested, of course, with UHP helium and obtained very satisfactory LODs. So in conclusion, we've got a table comparing the 3 different valve types that we discussed. If we're talking lifetime UHP applications, well, PLSV is definitely superior, 3 million actuations. Pressure drops, flow drops are both satisfactory for conical PLSV. Leak integrity is good for diaphragm valves with purges, but instead of impossible, I would have said excellent for PLSV. The same goes with crossport leaks. Dead volumes, again, are really good for conical rotary valves as well as PLSV. Inert treatments are possible with diaphragm PLSV as well. And then no peak shifting is observed with conical and PLSV. That pretty much does it.
All right, thank you, Felix. Are there any questions for Felix? I just have
One down there.
Oh, there you go.
Did you do any studies with very small injection loop volumes, say down to 1 micrometer, where a rotary valve can, over time, change injection volume?
Yeah, I wouldn't want to confirm. I believe so. Again, I haven't done these tests, but if you'd like, we can actually confirm. We can shoot them a quick email afterwards. But they've done, basically, this valve for them is not necessarily new. They routinely use it in their own platform, and they've started selling it to various suppliers. So I wouldn't be surprised that they've actually done some pretty small injections.
The error is going to be greater at hypertrophy.
Yeah.
But when you're doing high concentrations with low injection volumes is where you're going to have more error.
Right.
So how do you measure the inbound and outbound leak rate?
Okay, good question. Normally, they wouldn't measure it per se. They basically just want to prevent those leaks. But the fact that they capture the actual carrier gas used to purge the valve, they have included analysis of that train, basically, confirming leakage rate.
I mean, so you use the helium detector to check the read, or you use just based on the chromatogram, and then you determine the leakage?
Yes, okay, so
Which way you determine the, so say, I remember you said inbound, outbound, they have a 2 cc per minute or something leakage? What is the leak rate? I remember you mentioned at one time.
gotcha. So leak rate in this case is actually measured in terms of concentration. So they'll actually measure the, let's say, nitrogen in this case. So what's the lowest level of nitrogen that we'll detect with a zero gas? And this is basically inboard leaks in this case for the conical valve. And they track nitrogen through the actuation to see how much that varies through wear and usage of that valve. Am I answering that question?
You mean you based on you inject a certain ppm or whatever nitrogen in there, and actually you measure what is the output, and then so you compare the input and then the output. I mean, you compare with the low concentration, and then you give what actually the measurement. That's what you mean, and then determine what's the leak?
Yeah, they'd actually inject a nitrogen-free sample in this case, so something like pure helium, and look at the actual peak of nitrogen that shouldn't be there. And they quantify basically leakage based on the value of nitrogen that flowed inside the valve.
I mean, it's a little bit hard to believe, I mean, so have so much of a leak. But the leak is supposed to leak outside, right? The outbound. So when you say the leak is actually from port to port leak, I know it looks like you have some kind of piston on the valve. When you say the inbound actually, is it the port to port leak, or actually the leak to interferes?
Inbound or inboard actually would be basically nitrogen in the air, the 78% nitrogen that we've got.
Outside?
Yes, correct, exactly.
All the pressure, including carrier, it actually the pressurized, its pressure is much higher than the air. I mean, how can you can leak inside, into the system?
Yeah, partial pressures. Yeah, yeah. Yeah, exactly. And it's such a big difference of concentration, right? 78% in the ambient to basically no nitrogen in the sample, we do see through time. Any opportunity for a leak, you'll see nitrogen actually flow in, but we can discuss further, absolutely, if you'd like.
All right, thank you, Felix.
Thanks a ton.
There you go. All right, next up we have Daniel Merriman. Daniel is with Thermo Scientific, Senior Advisor on Marketing, studied electrical engineering at Hartford College in the UK. He's worked in the field of process analytics over 37 years, primarily in connection with mass spectrometry, since joining the VG Instruments business in 1988, before the internet. Now part of Thermo Fisher Scientific, since stepping back from full-time role, he's now the advisor of process environmental monitoring business of Thermo Fisher. Very passionate about football, soccer for those of us in the US. World Cup is coming to the US, right? US has a chance to win. And when not following, who said no? When not following Liverpool, he can be found out walking in beautiful English countryside or touring Europe with his wife in their RV. It's my pleasure to introduce Dan Merriman.
Does this work?
And that's the clicker.
Forward, just that one. Backwards. Backwards, okay. Thank you, Victor. And thanks, everybody, for your attendance, and to the organizers for giving me the opportunity to present again, which I think is my 5th presentation at this conference. And hats off to Felix. I mean, I have the benefit of having written the paper that's behind this presentation. Felix had to stand up and give somebody else's presentation. That takes a lot of nerve. I just have to remember not to fluff my lines. So today, I'm going to talk about ionization theory. So, you know, we come to the conference and we're not here to sell products, right? But, I mean, quietly, we really are. But today, I'm just going to talk about different types of ionization methods used with various types of mass spectrometry, purely for an informative discussion. And we'll start with the electron, which is fundamental to ionization methods associated with mass spectrometry. And I have today 4 different types of ionization method associated with different forms of mass spectrometry. Enclosed and open electron impact, and we have atmospheric pressure ionization, and then lastly, a brief introduction to the selected ion flow tube MS, which uses another form of ionization. And it starts then with Mr. Joseph John Thomson, or J.J. Thomson, who in 1897 published his work on cathode ray tubes, and it won him a Nobel Prize in 1906, as well as a knighthood from the UK government. And at the time, he noted that these particles, which were of the cathode ray tube, were smaller than an atom and carried a negative charge. That was his discovery, and they later became known as electrons, and they feature right throughout this presentation in the various forms of ionization methods for mass spec. So hats off to J.J. Thomson. So I'm going to start with the enclosed type of electron impact ion source. Process mass spectrometry generally uses this type of ionization method. Now, electron impact has 3 stages. We start with a cathode. Typically, a filament is used, a filament operating at a couple of amps current. It gets red hot. It produces thermionic radiation. So it produces lots of electrons. Now, the second stage is acceleration. So we accelerate electrons through the ion source enclosure where the sample gas will be present. And that's done by typically 70 electron volts. Now, the number of 70 electron volts is not just by chance or accident. It's chosen because it matches closely the amount of energy required to break organic bonds. So if you look at spectra produced by the NIST library, so you want to see what the mass spectra looks like, you generally go to the NIST website. They're usually referenced at 70 electron volts. But it doesn't mean that we always operate at 70 eV. There are some instances where we might want to either increase or reduce the amount of electron energy, either to encourage or discourage fragmentation of the molecule. One of the key characteristics of electron impact ionization is that in addition to producing molecular ions, it produces fragment ions very commonly. And it's fundamental to how process mass spectrometry is able to report the concentrations of complex gas mixtures, and we'll see this later. So these electrons are accelerated with typically 70 electron volts through the ionization region, and they're collected at an anode which is referred to as the trap collector. In order to increase the path length of the electrons as they go through the ion source and increase the probability of interaction with sample gas molecules, we usually have a small permanent magnet positioned perpendicular to the electron beam. So it's typically sitting behind the filament, and it means that it causes the electrons to move in this helical motion, and increasing the path length and increasing the sensitivity of the ion source. More ionization, essentially. And then thirdly, we have to push the resulting ions, the ionized sample gas, out of the ion source. So we have another small electrode referred to as the repeller, and it's placed behind the ion source, and that pushes the electrons to the exit slit of the ion source, where they're accelerated by ion energy. Ion energy varies according to the mass spectrometer type. If this is a magnetic sector mass spec, it's typically going to be working at about 1,000 volts ion energy, because you have a lot of energy to move the ions through the magnetic field to the detector. Conversely, if it's a quadrupole mass spectrometer, it's probably operating at 5 to 10 ion energy, 5 to 10 volts ion energy. This is what it looks like when it's constructed. Can't see much of the actual ion source chamber itself, because of course it's enclosed in the center. But what you can see are the pair of magnets that are situated top and bottom of this ion source. There are two of them because conventionally they're built with two filaments, so that if you get a unexpected failure of an ion source filament, the software can quickly switch to the second one, and you get continuous operation until it's time to perform routine maintenance. So, with electron impact ionization, it's producing molecular ions. So, you put in carbon dioxide and you get a CO2 plus ion. Similarly, you put in a propane sample, and those molecules will be ionized to C3H8 plus. But importantly, it also produces fragment ions, and it's because it produces fragment ions that it's able to, or it's used with process mass spectrometry to separate samples which have the same nominal mass. Now, you can get a mass spectrometer which will separate molecules of almost identical mass just by very high resolution. But they're typically very, very expensive, and they're used in the laboratory. So you get a mass spectrometer with a resolution of 10 or 50,000. You can separate carbon monoxide and nitrogen at the molecular ion. Great, it's all very good, but not very practical in the process industry. So what we rely on instead is fragmentation. Now, if you put propane and CO2 together in a gas sample, and you ionize it, and you make molecular ions of C3H8 plus and CO2 plus, it's going to give you absolutely nothing. It's completely useless in terms of separating those gases and identifying the relative concentrations. But fortunately, when you ionize propane with electron impact, you produce fragment ions. And in fact, the largest signal from ionized propane is at mass 29, so it's a fragment ion. Carbon dioxide is not going to produce mass 29, so this gives you a very simple insight into how gas mixtures containing molecules of the same mass can be identified by electron impact producing fragmentation. And in a practical example, this is our old friend flare gas composition. It's got 21 gas species ranging in concentrations from about 100 parts per million up to 60, 70%. And it depends fundamentally on the ability to see the different spectra for each gas component according to the amount of fragments, and the systems are calibrated so as to select ions or mass numbers which are preferential to the separation of gases within the mixture. Now, the second type of electron impact ion source is the open type. Now, with an enclosed ion source, as I just described, one of the fundamental preferences is to isolate the sample gas from the environment. So the ion source is sitting in a vacuum chamber, which is true for most mass spectrometers. And what we don't want is to have interference from the remaining gases within the vacuum system. So you're going to have trace amounts of air, you're going to have moisture and such hanging around in a vacuum system. We don't really want that to be present in our ion source in any great quantity. And we want to isolate then the sample gas molecules from the environment. So it's preferential to have this enclosed ion source. Now, an open source is usually used within a vacuum system where the purpose is to actually look at the presence of gases leaking into a vacuum chamber. So that could be a particle accelerator, a synchrotron, semiconductor production tool, maybe surface analysis equipment. Wherever you've got a chamber with a high vacuum and a risk of interference through gases or air leaking into the system. And they're referred to as residual gas analyzers, or RGAs. And so the purpose of being an open source is that it is open to the environment. We're not bringing sample gas into the mass spectrometer in this instance. The mass spectrometer is inserted into the process to sit and monitor the residual of gases within that system. So we want the ambient gases within the vacuum system, what's residual, to move through the ion source. Now, it still uses electron impact, so it's going to have a filament or a pair of filaments. It is typically less sensitive than an enclosed ion source. It produces fewer ions, largely because it's operating at lower pressure, but also because the electrons only get one pass through the ionization region. With enclosed ion source, the electrons have an opportunity to kind of bounce about a little bit in the ion source ionization region before they're pulled away by the vacuum system. In an RGA with an open type ion source, they get one pass through. So it's less sensitive, but it's a better system for monitoring residual gases in vacuum systems than an enclosed type. Now, the third type is different altogether. Now, the first two types are, but they're both electron impact type. They produce hard ionization, so they rely upon the fragmentation of neutral gas molecules to produce a spectrum that can be deconvoluted and is typically used for complex gas analysis. The third type is a chemical ionization method called atmospheric pressure ionization. Well, the clue is in the title. Ionization happens at around atmospheric pressure, and it occurs in a corona, which is produced by a needle held at a very high voltage, several thousand volts. So you have a very small area at the tip of this needle that I've colored in a little red circle there to indicate the place where the corona is generated between the needle and a flange containing a small orifice through which the resulting ions will pass. The first advantage of this type of ion source is that it's not necessary to precondition the sample. It's generally used for very high purity gas analysis. So high purity gas passes through the ion source continuously, and there's not really any preconditioning, maybe just pressure and flow control, that's all. The ionization happens in a very small area away from the influence of potential leakage points. And remember this, in this instance, the ion source is flooded with relatively high flow rates of very pure gas. It's chemical ionization, and it depends, or the ionization of each individual gas in the sample depends upon their ionization potential. So ionization potential is the amount of energy required to detach an electron from an atom or a molecule. So in ionization, you remove an electron from the highest occupied molecular orbit of an atom or a molecule. So the amount of energy required to do it is ionization potential. Now, this chart of ionization potential contains some gases towards the left-hand side which have high ionization potential, and others towards the right-hand side which have a lower ionization potential, meaning that they are easier to ionize, require less energy. It so happens that the gases over to the left-hand side are very often used in the semiconductor industry, either for purging semiconductor wafer fabrication tools or for annealing processes. And the gases over to the right-hand side are the contaminants that they don't want to see in their sample gas, in their ultra-high purity gases. So it's just fortuitous that this technique lends itself to the detection of impurities at very low concentrations in gases used in the semiconductor industry. And by low, I mean parts per trillion and parts per billion concentrations. Now, the IP table that you see here is favorable for some gases. I mean, it's great to measure oxygen in helium. Oxygen has very low ionization potential, helium very high. But some of the gases clustered together, like argon, nitrogen, hydrogen, are less favorable. They don't have such a differentiation of their ionization potential. And high-purity hydrogen is one of those target gases used in the industry to which this is mostly applied. Thankfully, there's another phenomena, which is proton affinity. And this table describes the probability of different atoms and molecules to gain a proton from ionized hydrogen. So at the bottom of the table, you have those gases which have high proton affinity versus the gases at the top of the table that have a low proton affinity. And again, fortunately, to this analytical method, the gases at the bottom often are the target impurities that the semiconductor industry wants to see. So in this process, pure hydrogen is ionized. We make H3 plus ions, and then due to proton affinity, a proton is given up to a neutral gas molecule or neutral atom, and then the hydrogen returns to its original state. And as I said, it has a practical use as well. Very, very low concentration detection in pure gases. This example is oxygen in nitrogen. So it's a calibration graph for oxygen. The concentrations that you can see on the x-axis are in parts per billion. So it starts at about 9 ppb and goes all the way down to 0. The signal size generated at the detector of APIMS in this case is about 3.5 10 to the minus 16 amps per ppb. The background concentration at the ion source is only 6.3 parts per trillion, and it's measured, this oxygen concentration is measured with a standard deviation of 0.9 ppt, or 900 parts per quadrillion, if you prefer, with almost perfect regression. So a very, very practical utilization. And the last example is another ionization method applied to a mass spectrometer type called SIFT, or Selected Ion Flow Tube. This fourth type of ionization method is again a chemical type, but unlike APIMS, where APIMS ionizes the customer's sample gas, and that gives up its charge to impurities, or it gives up a charge to the impurity by proton affinity. In this instance, we introduced the application of reagent gases to produce ions which can later react with the sample gas to produce ions of a particular mass number that can be used to differentiate from others within the sample. Now, the initial ionization is commonly microwave discharge. But this ionization method actually uses a quadrupole mass filter in the ion source itself. So this is a mass spec with two quadrupole mass filters. The first one is simply to separate or select the preferred reagent, which is going to be used as a reactant with the sample gas. So in SIFT or SIFT, the selected part means that it's using a mass filter to select a preferred reagent. And then downstream of that selection, you have the flow tube where you get a reaction between the reagent ions, the sample gas analytes, and that produces product ions and neutral molecules or neutral atoms. Downstream of that, they pass through a conventional quadrupole mass filter and are measured in the conventional way. The use of multiple reagents and the ability to select reagents according to each sample gas and each target analyte means that they're a little bit more versatile to measure some gases at particularly low concentrations. So one of the claims of this technology is that where a conventional quadrupole mass spectrometer, or indeed a magnetic sector mass spectrometer, might measure organic gases in ambient air in the ppm or ppb region, this will measure the same target gases at an order of magnitude lower. The other claim of this type of mass spectrometer is that it can operate without calibration, and that claim is made because the reaction kinetics are very well understood, and it's possible to control the reaction time very closely. Now, that's probably true in a laboratory environment, but even manufacturers of SIFT would admit that variations in analyzer construction and sensitivity and reaction efficiency mean that ultimately they still use validation and calibration like most other kinds of analyzer. So in summary then, there are lots of different types of ionization method. They vary according to the application need, and they're applied to different types of spectrometer for different applications. From the simple electron impact ionization, which is still the workhorse of process and residual gas analysis mass spectrometry, through some more recent novel types of ionization, such as APIMS and SIFT. And for that, I'll thank you for your attention.
Thank you, Dan.
And take questions if there are any.
Yeah, any questions for Dan? All right. Thank you very much, Dan. Appreciate your time.
Thank you.
All right, next up is Dr. Matt McCormick. He is the CTO, Chief Technology Officer at Spectrum Environmental Solutions based in Austin. His educational background consists of a BS in math and physics from Rose-Hulman Institute of Technology and a PhD in physics from UT Austin, specifically related to high energy density plasmas and laser optical design. After graduate school, he transitioned to learning about optical instrumentation used for gas phase molecular spectrometry, primarily FTIR and IMAC LLC. He then joined Spectrum shortly after its founding in 2017 to be a senior scientist, expanding his knowledge of spectroscopic methods, including UV, DOAS, and Raman, while also assisting in the overall system design of the instrumentation. In 2021, he was promoted to CTO and charged with spearheading the technological growth of Spectrum, primarily by overseeing major redesigns of current offerings, reviewing overall project designs, and developing new instrumentation to meet customer needs. Thank you, and Matt, take it away.
All right, thank you. Good afternoon. Hopefully I can keep everyone's attention when everyone's stomachs are grumbling for dinner here in a little bit. Today, I'm going to talk about enabling faster response of measurements of ethylene oxide using a new implementation of a new technology that's been around for a little while, and show some results that we have achieved in a real situation. So, to start with some background, ethylene oxide is a pretty important chemical in various applications. It serves as an intermediate in the production of various compounds as well as detergents and solvents, and it's a very major use in antiseptic sterilization facilities for medical equipment and those types of things. I was also interested to learn that it's used to produce a component in lithium-ion EV batteries. So for a chemical that's, maybe thought to be just a chemical industry product, it's actually used in technology for the future, for our kind of green going forward. So that was interesting to learn. Since it's used as a sterilization compound, you can imagine it's very toxic, and it's gained some maybe increased scrutiny in the past 3 to 5 years as agencies have tried to determine what are safe exposure levels and clamping down on emissions from sterilization facilities into the areas around them. So there are EPA rules, the HAN and NESHAP, that are trying to put limits on emissions from these facilities. This Fungicide Insecticide Act wants to reduce exposure limits by an order of magnitude over the next 10 years. And then state agencies that have sterilizers in their jurisdiction are also coming up with their own rules for what are acceptable emissions from these facilities. And so, as I'm sure a lot of us know, rules are words, okay? Rules can say more or less whatever they want, but if you don't have technology that can meet the rule, what good is the rule? That's kind of my opinion. And so, to add to that complexity, if you have a rule that has a very stringent emission requirement or so on and so forth, what are you going to do to meet that rule? Well, in this case, the EPA established Method 327, which uses these canisters to slowly collect ethylene oxide, if it's present, from the ambient air at facilities, fence lines that either use or produce ethylene oxide. And while you can get very good detection limits that way by essentially concentrating many hours or even up to a day's worth of gas, you lose time resolution. And so it's this multi-hour or day-long average, very analogous to the passive tubes that are used for benzene fence line monitoring. I mean, that's 2 weeks worth of averaging. So you can have very good detection limits, but what are you going to do with that data? for one, it's a long collection time, and then you have to send the canister to a lab, wait a couple of days to get the analysis, and then it's almost a week and you get a result that's out of compliance, and then it's like, well, what happened? I don't know what happened. What even happened that day? So there are many cons, I believe. So I've covered a few of these, and on top of that, since it is a time-averaged measurement, you don't know if you collected a nearly constant background concentration or if you had maybe one very short-term release that was higher concentration. So knowledge of where the ethylene oxide came from is pretty minimal. And then as all analytical techniques have, they have their biases and interferences and difficulties, so this is not immune to that. And then it's labor intensive. You have to have someone go to the fence line, get these canisters, send it to a lab analyzes it, take them back to the field, and so on and so forth. The cycle continues. So how would we try to address these maybe limitations of this method or improve upon them? So you'd obviously want to improve the sampling time to much shorter time resolution. Get your results ideally as it happens or in near real time. If it's a fence line application, you could pair it with metadata to try to help locate the source if it is like a leak or some kind of release that's triggering these measurements. And then, the canister bias issues, if you are careful with how you handle the sample, you can minimize those issues. And then if you have an instrument that can run more or less autonomously, you reduce your labor issues. So, could something like this exist? I would say the answer is yes. For those of us who are familiar with infrared spectroscopy, you might know that ethylene oxide has a pretty strong absorbance feature in the mid-IR, and we can exploit that for very good sensitive measurements. And with a laser, we can perform an analytical technique called wavelength modulation spectroscopy, which has been around for probably at least 20 years in academia. And it has the advantage of being a little bit more sensitive than traditional FTIR or other absorbance spectroscopy methods, which I'll describe in a little bit how that's possible. By using a laser, it's very high resolution, and so you can help minimize spectral interferences from other molecules that absorb in the same region. You can have much faster response with the high optical power, lower noise, continuous sampling of the gas through a gas cell, and so it looks promising. And the laser that would work in this spectral region is called an interband cascade laser. I'm not going to describe how it works, but it's basically a little semiconductor type laser where you pass current through the emitting element and it emits wavelength, a certain wavelength based on that current amplitude. Another nice advantage is that since its wavelength emission depends on the current, you can, by varying the current you put through the laser, you can scan across a somewhat narrow band of the infrared spectrum, about 7 to 10 wave numbers. So you can scan across one or more spectral lines and get very high resolution measurements. Now you can use a similar type of detector you would use for FTIR, for example, like an MCT, to get high sensitivity. And then while you could actually perform typical direct absorbance measurements, if you modulate the laser at high frequency of a few tens of kilohertz, you can enable this wavelength modulation spectroscopy measurement. So at a high level, this is how this measurement is performed. You start with a function generator that generates a sawtooth ramp that would scan the current going to the laser. And then you add on top of that a low amplitude, high frequency modulation. And this signal gets fed into the laser controller, which converts that voltage into the current that gets fed into the laser. The laser emits the wavelengths as determined by the current that's being fed. The light goes through a multipass gas cell, and then the resultant light falls upon the detector, is measured, digitized, sent to a lock-in amplifier. The lock-in amplifier, as the name implies, kind of locks in on the modulation frequency. And this enables good filtering out of noise that would contaminate maybe typical direct absorbance measurements, like vibrations and other types of noise. And in doing this, after the lock-in, you send the digitized signal to the software, which analyzes the spectrum and quantifies what's there, or if it's not there for that matter. In this case, we are looking at not the fundamental frequency that we're modulating, but we're doing a second harmonic measurement. So using the higher harmonics further improves the noise rejection to improve the sensitivity. So here's a view of the internals of our instrument. At a high level, it's kind of simple. You take your laser light, send it through a couple of mirrors into the gas cell, and the gas cell is designed to produce about 20 meters of optical path. After passing through the gas cell, it goes to the detector and goes through the process that I described on the previous slide. The path length was chosen to be able to achieve a detection limit in the hundreds of parts per trillion range. And we'll see if we achieve that here in the coming slides. As I said, this technique's been around for about 20 years, but it's really been reserved in the academic world. It is a very sensitive measurement, and I don't know if it's what's kind of kept it from being commercialized, but I think maybe it's the lasers have become more commercially available or other techniques. I don't know for sure, but we went to great lengths to try to make the instrument robust and industrial. So now here we get into the interesting stuff, the data. So here are some measured spectra of the ethylene oxide, which is a very small wiggle in that top right plot. And then next to it is methane. And then down in the bottom right is water. And so you can see that water is a pretty major interferent or potential interferent with this measurement. You can see the y-axis on those plots. You know, you've got a few orders of magnitude in those signal strengths. So are we going to be able to see it in the water? Well, stay tuned. So now that we have measured the spectra, we can do a detection limit evaluation. Now, in academic research papers, a typical way that they present detection limits is through the use of this Allen deviation plot. And basically, it's a measurement where you take many very short duration measurements and do some analysis on that to try to determine the optimal averaging time and then what your sensitivity would be at that optimal sampling time. Because there are different types of noise in measurements. Some noise averages out very nicely. Some noise, there's a limit to how much you can average out. And after a while, it eventually kind of takes over and you can't, it actually makes your measurement worse. And so when we do this analysis, it predicts a detection limit of 30 parts per trillion, which sounds great, right? You'd love to be able to measure 30 parts per trillion. But when I know what the amplitude of the absorbance is, and when I compare it to what the noise level of the instrument is, I just don't see that as being a realistic claim. And so, and I've seen many papers that do this, and I don't think I've seen one where the Allen deviation matched what I saw in the data. So I put this up because it's a very common thing with this type of measurement, and as I'm sure some people have run into, you know, there's claims of detection limits and then there are real detection limits. And so, you know, you always have to kind of take it with a grain of salt. We try to be very careful about this, and we'd prefer to use ASTM methods for evaluating detection limits. So there's two kind of main ways. The first one is essentially a noise-limited value, where you take consecutive measurements back to back. If you were doing FTIR, you would ratio them against each other, look at the absorbance, and calculate what the detection limit is. In this case, we subtract them. That's just the way it works. And we get about 90 parts per trillion, which is, I think, more realistic. Another way of doing it is through these other MDC2 and 3 calculations, which are at a high level trying to quantify how well your analysis algorithms are analyzing the data. And in this case, we have about 300 to 400 parts per trillion. And this looks a little more realistic to me. So let's see how this compares to our real data here. So here are some measured spectra at lower concentrations. So we've got 16, about 1.5, and half a ppb. And even the half ppb is still pretty clear. The blue lines are fits to the measured yellow lines, and then the red in the bottom plot of each section is the subtraction, or the residual, I suppose I should say. So you can see they fit pretty well, and they're pretty clearly verifiable. So this is encouraging. Now, those of you with sharp eyes will notice that we're measuring this in nitrogen still, okay? So it's great that we can measure this in nitrogen. Will we be able to measure this when water is present? To help try to determine that, we fielded the instrument at a commercial sterilization facility, and we have an FTIR installed as a SEMS at that facility, monitoring their exhaust from the thermal oxidizer that destroys all the ethylene oxide. And we coincided that deployment with the performance of a RADA test on the installed SEMS. So this was to help demonstrate the accuracy and precision of the instrument and evaluate, how sensitive it really is in a real industrial application. And so here's the RADA test results. So the spike gas was about 2 ppm of ethylene oxide. When we, based on the dilution of the CF4 as measured by the FTIR, the target dilution concentration of the ethylene oxide was about 180 parts per billion. And there's 10 20-minute tests followed by 20-minute zeros. And the criteria for passing is a plus or minus 10% of the target value, and it passed all 10 tests. This is good. Now, you may notice, if you have really sharp eyes, that at the baseline, there's a little bit of a bias in the first 4 or 5 0 points. So if we zoom in on those, we measured about 1 to 1.5 ppb in the first 3 0 tests, and then it trailed away to 0. And when we showed this to the facility, they told us that they had actually run a sterilization cycle early that morning before we did the RADA. And so what we were likely seeing was the residual getting through the thermal oxidizer. And so the fact that we were able to see this in real measurements was very encouraging. And they were quite excited to see that, actually. So, so that was a nice, unexpected result. And now, since this is optical spectroscopy, we can validate these measurements. So if we pulled a few of the spectra, either going up or coming down those tests, and then some of the zero measurements. And, the higher concentration ones are very clear with high R² values. And then even the 1 ppb measurement is still pretty clear. And this is, again, this is with water present in a real sample. And again, the MDC detection limit is about 300 parts per trillion. And this is a live detection limit as calculated by the software. So this was a really, really encouraging result. One last thing I'll show is the morning of the RADA, there was a rather unexpected event where the thermal oxidizer, I think, overpressured and shut down. And there were ppm level ethylene oxide coming out of the thermal oxidizer. Well, it reset, but the chamber didn't come back to its normal operating temperature. I think it was like 20 or 30 degrees below what it should operate at. And so we measured about 200 parts per billion for almost an hour, 45 minutes. And then they had to recycle the power on the thermal oxidizer and reset it again. And again, we saw a big spike of ethylene oxide, which trailed off to 0 because it came back to temperature correctly. So this was a nice demonstration of the responsiveness of the instrument to even high-level, ppm-level ethylene oxide. But then to have it go back to 0 very fast was very nice. And it just showed that you were seeing near real-time measurements. So yeah. With that, I'll wrap up. The regulations, as I'm sure those of you who deal with ethylene oxide know, want very low detection limits, but in order to achieve those, they are sacrificing the time resolution. And you know, this produces data that I would say is not very actionable. And so there are other techniques. You know, I've mentioned FTIR. There's also cavity ring down. Those are alternative measurements. The FTIR, for example, is, I think it's got about 10 ppb detection limit, so it's not quite as good. But this new laser-based instrument we've demonstrated has detection limits of about 300 parts per trillion in real ambient air samples. So it doesn't have to be dried out completely. Water can be present. And it's a relatively simple instrument. And again, since it's a spectroscopic measurement, we can validate the data pretty easily. So that it would be defensible for regulatory needs if need be. So that is what I've got to say. And thank you for your time, and I'll take any questions.
All right, thank you, Matt. Here's your gift. Thank you very much. Any questions for Dr. Matthew? No? All right. Well, folks, thank you very much for being, oh, there's a question over here. Yeah, we got the microphone right here.
So fantastic work. Congratulations.
Thank you.
Looks really nice. I was just wondering, does the market need an instrument that goes that far? So we are in PPT level, ethylene oxide. I would say it's better than anything. So is the detection limit in PPT really needed? Why have you developed something so good? That's my question.
It's a good question. So there was a study, and I can't think of the name of it, but it was done like 5 years ago, I believe, where they, based on like toxicology and stuff like that, they were pushing for a permissible exposure limit of something like 10 parts per trillion. And it was a major decrease from what had been accepted for a number of years. And there was a fair amount of pushback about, is that a really achievable detection exposure limit? Can you measure that low, and so on and so forth? And so that was what I kind of alluded to in my early slides was there's been a lot of kind of debate, I guess, within EPA and state agencies about like, yes, it's toxic. Yes, we should limit, emissions and exposure, but, what's an acceptable exposure level? And, there are plenty of compounds where certain states say, the exposure level is X, and another will say the exposure level is Y, and OSHA says it's something else. And so there's, it's hard to get really uniform agreement, I think, and it's not just for ethylene oxide. So we tried to do the best we could, but have it be something that was not academic, essentially, that is like so super sensitive you can't use it, but it's still sensitive that it's practical for most kind of applications, I suppose. That's my high-level answer. If you'd like to talk more, feel free to stop by. Yep.
Any other questions? All right, well, thank you very much. Folks, this is our last presentation for the day. Thank you very much for attending. You have some papers there in front of you. If you could fill those out and turn them in, we would appreciate it. Thank you.